Our brain cells learn by being active. So the more they fire, the more they wire, right? You start off in early life, and a lot of my research is on the neonatal brain, where we've been looking at the neonatal brain is practically another different species compared to the adult in terms of the chemistry, the types of synapses, and the cell populations. And this has implications, of course, for the kinds of medicines you'd want to give a neonate compared to an adult, because that's a good example of two big extremes. That adult drugs don't necessarily work on a baby brain because the targets aren't even there yet, right? So this process begins in the neonatal period, and in the first few years of life, you think about the amount of learning that happens. You have a baby that has poor vision, has no ability to control its body, and can't speak. Language is acquired, fine motor coordination over just a few years. And that process is due to synaptic plasticity, the molding of the brain by use and experience and practice. So synapses, which is where brain cells are connecting, are actually at very high levels in the immature brain. And the proteins that are present for creating this synaptic plasticity are programmed to be at higher levels. So children can learn effortlessly. And that takes excitation. Our brain cells learn by being active. So the more they fire, the more they wire, right? And this actually is very interesting because children's brains are more excitable than adult brains. We have a balance between excitation and inhibition, meaning turning on and turning off. Every brain cell has a combination of those inputs. And the children's brains have less inhibition compared to excitation for the reason that they want to have this activity-dependent synaptic molding plasticity. This is also a double-edged sword because, of course, epilepsy, for instance, which is a disease of too much activation at synapses, is at much higher levels of incidence, at least during childhood, than later in adult. So we can understand how diseases have these age-specific patterns also in thinking about the brain. So anyway, the child's brain has more excitation than inhibition, and it slowly comes up through the adolescent years so that there's a balance of inhibition. Of course, our frontal lobes use a lot of inhibition. There's a lot of impulse control that requires inhibition when you remember to be tactful, for instance, and not blurt something out. So the adolescent still has more excitation than inhibition. In the meantime, where we're wiring our brains, the myelination is taking quite a long time to finalize the process. And there was a study done by Jay Geed and others at the National Institutes of Health where they've used functional imaging and something called diffusion tensor imaging to look and track how brain areas wire together. And this is really recent information that's from a cohort that they've been following from early childhood. And you watch these beautiful images as they do time lapse and show that the brain sort of connects from the back to the front. And still in your early 20s, it's not completely done yet.